Today we will dive more into types of sequences and how to come up with the recursive and explicit formula. Before you, I have a sequence written out already. 3, 8, 13, 18, 23. I notice that this is an infinite sequence because it continues on forever with the dot, dot, dot. Then I also start to notice that there might be some pattern developing here. Now, here's term a sub 1 and a sub 2. Let's do something. Let's take a sub 2 minus a sub 1. And what do we get? 8 minus 3, which is 5. Now let's look at a sub 3 and a sub 2. A sub 3 minus a sub 2, well, that's 13 minus 8, which is 5 also. Well, then a sub 4 minus a sub 3, well, that's 5 also. And then continuing on, there's a pattern here. What we did here is we found the difference between two successive numbers in our sequence. Now, if that difference is all the same, the difference between these two numbers is 5, here's 5, 5, and 5 again. If that difference is the same, that is said to be a common difference. Now, if we have a common difference amongst the successive terms in the sequence, that sequence is a special type of sequence, namely an arithmetic sequence, sometimes called arithmetic sequence, obviously. And the arithmetic sequence is when successive terms have a common difference. Now let's go back to our previous sequence, because besides defining that this is an arithmetic sequence because there is a common difference, it means the difference between each successive numbers is the same. Our goal today also is to try and come up with an expression, a formula for our sequence. Now, if I look at this, I can recursively say that we started with 3, and then we added 5 to get the next term. And then from that term, we added 5 again. And from that term, we added 5 again. So recursively, I can say that I started out a sub 1 is equal to 3. And for each value of n greater than 1, a sub n, we can say we take the previous term, which would be a sub n minus 1. Remember, that is how we say previous term. And then I'm adding 5 to that value. So this is a recursively defined function. We know a static initial value and then how to find out any successive term. And again, this is for our n values greater than 1. We use this formula here because we already know a sub 1 is equal to. But this doesn't really help us come up with the explicit function or the explicit equation that will help us find any term independent of another term. Now, to come up with an explicit function for this sequence, we're going to analyze the sequence a little bit more. First term is 3. How do you get the second term? 3 plus 5. How do you get the third term? 3 plus 5, and then you add 5 again. How do you get the fourth term? 3 plus 5. Plus 5 is the third term, and then you add 5 again, and so on and so forth. Now, if we look at what's happening here, pattern is developing where we're repeatedly adding the number 5. Here we have 0 terms of 5 added, 1 term, 2 terms, 3 terms, 4 terms, and then 5 terms of 5 we'll add on to the number 3. So I have 1 times 5. plus 3. We have 3 plus 2 times 5 because we represent repeated addition as multiplication. 3 plus. Now I have 3 factors of 5 that I'm adding. Again, there's a pattern here. I have 0 factors of 5. Now if we simplify this down into variables for any sequence, we could say that the explicit sequence for this one would be, say, a sub n equals our initial value, a sub 1, which is 3, plus, well, it looks like we're multiplying by 5, which is actually our common difference. Now, how many factors of 5 do we have? Well, we have 0 here, which is term 1. We have 1 here, which is term 2. We have 2 here, which is term 3. So it looks like we have n minus 1 factors of 5 that we're going to add to 3. This will be my explicit equation, explicit function that describes the sequence. It allows me to get any term independently of a previous term. So if I wanted, say, term a sub 100, that would be just our initial value plus 100 minus 1 factors of 5. Which is equal to 3 plus 99 times 5, which is equal to 498. Look at our function again. A sub n is equal to our initial value plus n minus 1 times our common difference. So looking forward, the general term for any arithmetic sequence is a sub n equals a sub 1 plus n minus 1 times our common difference, which we label as d. There, that looks better. Okay, let's look forward to a problem. Here's a sequence, infinite sequence. Let's see if the sequence is an arithmetic sequence. If it is, let's write an explicit function for this sequence. All right, let's see if there's a common difference, because that is what an arithmetic sequence has. Okay, 5 minus 8, well, that would be negative 3. 2 minus 5, that looks like negative 3. Negative 1 minus 2, negative 3. And finally, it looks like negative 4 minus negative 1 would be negative 4 plus 1 is negative 3. Well, it looks like there is a common difference with each successive term in a sequence. Therefore, yes, this is an arithmetic sequence. Now, let's find an explicit function for this arithmetic sequence. Well, that would be a sub n is equal to a sub 1 plus n minus 1 times our common difference. Well, a sub 1 is equal to 8. N minus 1 is going to stay the same because that's how you get the terms in your function. And we look at our common difference, which is d, and our common difference is negative 3. Now we can simplify this expression a little bit. We can distribute negative 3 through and come up with a more simplified version of our expression here. So 8 minus negative 3n plus 3, which is then equal to negative 3n plus 11. Now, if you look at this expression we came up here, negative 3n plus 11, you notice that's a linear function, and that should make sense because we're just, for every one move over in our terms, we are going down negative 3. So it would look like a slope of a line, or it would look like a graph of a line. Should make a lot of sense. And I say, hey, Mr. Bonley, which way should I write this expression? Well, this way, right here, is useful because it tells us what our first term was, our a sub 1 term, and it tells us what our common difference is. However, this expression is neater and easier to work with. I know it doesn't answer your question, but hey. All right, let's take a look at another sequence. Is the sequence arithmetic? Well, look at common differences. 4 minus 1 is 3, 9 minus 4 is 5, 16 minus 9 is 7, 25 minus 16, well, that's 9. Well, right away you're saying, nope, that is not an arithmetic sequence, and you're correct. But let's take this a little bit further. This is called the first level common difference. And you can see that there's a pattern with the first, or I shouldn't say that, it's not a common difference. You can see that the first level differences are not common, but there is a pattern with these first level differences. Let's take a look at it. 5 minus 3 is 2, 7 minus 5 is 2, 9 minus 7 is 2, and if we look at these second level differences, they are common. Before, for an arithmetic sequence, if the first level difference was common, it was a linear function. The power on your x is 1. If we look at the second level differences, and they are common, that means this would be a quadratic function because the power on x would be 2. And by inspection, if you look at this, that makes sense because the first term is 1, second term is 2, which looks like second term is 4, which looks like it is 2 squared. Third term looks like it's 3 squared, and 4 squared, and 5 squared. So it does make sense that the second level common differences are the same because the function is a quadratic. Okay, let's look at another sequence. A sub 1 is 2, 4, 8, 16, 32. Let's check to see if there's an arithmetic sequence. 4 minus 2, well, that's 2. 8 minus 4, well, that's 4. Nope, this is not an arithmetic sequence. Well, let's see if there's another pattern going on here. It looks like everything's just doubling, as you can clearly see on this infinite sequence. Let's look for a ratio. What's 4 divided by 2? A sub 2 divided by a sub 1. 4 divided by 2 is equal to 2. Okay, a divided by 4. You can clearly see that's 2. 16 divided by 8. Well, that's 2. About 32 divided by 16. The next term divided by the previous term. Well, that's 2 also. Well, we have a fraction right here. That's called a ratio. It looks like all the ratios are equivalent. All of the ratios are common. We have a common ratio of 2. If a sequence has a common ratio, that is called a geometric sequence. Definition for a geometric sequence: successive terms have a common ratio. For instance, a sub 2 divided by a sub 1 is equal to a sub 3 divided by a sub 2. Now let's look back at that previous sequence. Let's try and come up with a recursive formula to help us come up with the next term. Well, it looks like we're starting with 2, and then for the next term, we take previous term times 2. Well, then the previous term times 2. Previous term times 2. And so on and so forth. So for recursive function, it looks like a sub 1, our first term is equal to 2. Now how do we come up with each term after our first term? A sub n was equal to previous term, a sub n minus 1. And then times 2. We could put parentheses around this or this also to clear up some of the clutter, if that would help. So this is our recursive function. Again, the second part is only when n is greater than 1, because we already have a sub 1. Now let's come up with explicit formula. That one's easier. That's easier to come up with term 100, a sub 100. Now, listen, analyze the terms here. We have 2, and then we have 2 times 2. Then we have previous term, which is 2 times 2, and then our previous term, 2 times 2 times 2 times 2 again, and then so on and so forth. If you look at what's going on here, we have the value 2 here, 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 which is our initial term. It looks like we have 0 factors of 2 being multiplied. Here's 1 factor of 2, and then 2 factor of 2's, 3 factors of 2. Then they're multiplying, so how you represent repeated multiplication as a exponent. So it looks like we have our initial value, which is 2, times the base 2, because this is doubling, just like we've looked at in some of our previous work. How many factors of 2 do we have? We have n minus 1. Now here's our explicitly defined function for our sequence. What would any function look like for any geometric sequence? Well, a sub n would be equal to your a sub 1 value times your common ratio, we'll call r, raised to the power n minus 1. Now let's look at this particular sequence. Let's see if the sequence is geometric, or maybe it is an arithmetic sequence also. And if it's an arithmetic sequence, let's find the common difference and write an explicit function for it. If it is a geometric sequence, let's find the common ratio, and then we'll write a function for that one also. Well, obviously, by just close inspection, we can see we're not adding to get to the next term. So there's not a common difference. Well, let's see if there's a common ratio. Let's take a sub 2 divided by a sub 1, which would be 21 divided by 7, which is 3. Okay, 63 divided by 21, well, that's 3. 189 divided by 63, that's also 3. So we do have a common ratio. Common ratio is equal to 3. Our initial value, a sub 1, is equal to 7. So our explicit function that defines this sequence is a sub n equals 7 times our common ratio, 3 to the n minus 1 power. Now I can use this function to come up with any term in this particular sequence.